Okay, hello everybody. I'm Richard Southwell, and today I want to talk about Notepad. So, you might not have thought of Notepad as something which features particularly highly in the world of networks and complexity, and in many ways that's true. I think Notepad is really the kind of workhorse of text manipulation software. Nevertheless, today what I want to do is to use Notepad and use the ridiculously simple functions that Notepad provides to actually generate some kind of complex behavior. And the way I want to do this is to use some string rewrite systems. So the thing is with Notepad, the kind of redeeming feature is that Notepad has a kind of function called replace. So let me just give you an example of this replace working. So if I type in catfish, spell it right, catfish, cat, let's say, I can do a replace on this. So if I just, I think Control H is the shortcuts, and if I type replace cat with dog, then if I replace all, there I go, I get dogfish dog. So this command is scanned the entire document, replacing every instance of cat with dog. And you'll notice that many different kinds of text manipulation software have these kind of functions. So what I'm going to talk about today is not specific to Notepad. You can do it on Word, you can do it on LaTeX, you can probably do it on loads of OS things. You can do this kind of thing using many different text editing software. Anyway, what we're going to do now is we're going to use this very simple kind of replace all command to make some dynamics happen. So let's just look at a really simple example. We'll use binary because it's easy to think about. So we're going to start off with 1, 0, and these are going to be our replacement rules. We're going to replace every 1, 0 with 0, 1, 0, 1. So let's go. Replace all. Here we are. This is after one iteration, and we'll just keep iterating. Keep pressing replace all. Every time we replace all, it scans the string for these and replaces them with these. So you can see here that the pattern we're getting out is really pretty simple. Actually, we'll just have a quick look on Mathematica. I've done a little bit of more sophisticated kind of visualization here. So the grey blocks, they're zeros, the black blocks are ones, and time's reading downwards here. So what this is showing are the successive strings over different time steps. Okay? So this is really simple kind of dynamics that we're seeing being produced. So a good question then is, can we get any more kind of intricate or interesting dynamics out of these kind of simple Notepad-based systems? So let's take a look at a pattern with some more interesting kinds of dynamics. Here we're just going to start with a single 0, and our rules are going to be to replace every 0 with 1, 0, 0. So let's go. These are the first few patterns. over the first few time steps. And you can see already that what's coming out here is not quite as simple as what we saw before. If I run it for a few more time steps, I think it rapidly becomes too confusing to really get your head around in this kind of Notepad format. And so a good way to look at a pattern like this is to move it into something like Mathematica. So here at the top here we see our different strings on different time steps, and below we've made this kind of graphic representation with grey blocks representing zeros, black blocks representing ones. Okay? And if you look at this picture for a while, you'll see some evidence of a kind of nested structure which is appearing from this rewrite system. So for example, we have a couple of double stripes and then quite a thick black stripe, and then we have 4 of these double stripes and then an even thicker black stripe, and then counting from the beginning we have 8 of these double stripes and then an even thicker black stripe, and then we have 16 of these double stripes and then an even thicker still black stripe, and so on and so forth. So generally I found, at least through my expertise in combinatorics and things, that once you start seeing powers of 2 appearing in these kind of patterns, it usually means that there's quite a simple way to crack the system. Now, I haven't actually cracked this system and figured out everything it's going to do, but I imagine it shouldn't be too difficult. It looks to me like there's some fairly convincing nested structure behind this, and that using the right kind of recursion and inductive arguments, one could sort of derive an exact formula for what this system does. So let's just recap. The first Notepad system we looked at, if you like, the first non-overlapping rewrite system with one rule, that had really simple trivial dynamics. Now, this system here, this has kind of nested dynamics, a bit more complicated. And who knows, it could have more complicated still dynamics if we put some more interesting initial conditions in. Actually, I doubt it. In this case, I think everything grows so fast that there's no real space for intercommunication. But anyway, we've seen an example of a real simple system and an example of a kind of nested or fractal pattern making system. So what else is there? Are these our only possibilities? Well, if you have a look at my paper on more general systems like this, which involve more different rules, you can see loads of examples of loads of different kinds of rewrite systems which are more interesting. But here, because we want to interface with Notepad and everything, we're really just restricting ourselves to systems with just one rule. Just one rewrite rule. Replace this kind of string with that kind of string. That's all we're allowed to say. So, in that case, can we find anything more interesting? Well, I think I have. I did a search through the sort of simplest possibilities, and the first rule I found, which seemed to have really interesting behavior, is as follows. So our next complicated rule, the one with really seemingly complex dynamics, it goes like this, basically. We just start off with 1, 1, 0, and then we keep applying these replacement rules here. That's replacing 1, 1, 0 with 1, 0, 0, 0, 1, 1, 1, 0, 1. So let's just see what happens when we evolve these rules. Again, very quickly, we end up with a very long string, and it looks kind of complicated, and it's difficult to really decide exactly what's going on here. Is this really random? Is there some hidden nested structure? Who knows? Well, a good way to understand more about that is to look at one of these kind of two-dimensional plots here. So this is such a plot, and the string is going from left to right, and time is going downwards. So this is our original string, 1, 1, 0. And you can see immediately just from this picture that the strings getting produced are really very intricate. They seem to have some kind of repetition if you read diagonally downwards, but it also seems as if as one moves right, more and more intricate forms are being produced. So here enters the age-old kind of question when analysing systems like this. Is this system truly complicated, or is there some kind of hidden regularity? Is there some kind of magic formula which crushes all of this system up into something that's really easy to understand? And the answer is, I don't know. In fact, it's a funny old thing, because in scenarios like that, really, the only way one would know if such a compression was possible would presumably just be to find such a compression. Anyway, we haven't found any ways to simplify this. It appears rather complicated. And another way that one can verify that something fairly sophisticated is going on here is to just sort of do some more sophisticated ways of analysing the data. For example, here I've taken the string generated after 16 iterations of this rule, and what I've done here is I've had this line go down by -1 every time a 0 is encountered, and up by 1 whenever a 1 is encountered. So the way that this line bobs up and down reflects the sequence of 1s and 0s in the string. And you can see that this is a fairly intricate pattern. There is some kind of evidence of nesting. For example, over here we have these few spikes and then a bigger spike, and we seem to have the same kind of pattern over here. So there's definitely some kind of repetition here. Sorry, over here. So there's definitely some kind of repetition here of particular sub-patterns, but whether that means that the entire thing is reducible or not, I'm not sure. In fact, my kind of gut feeling is that this is actually a properly complex system with components which are kind of fundamentally difficult to understand. So this system was found basically by searching through the space of string rewrite systems just involving one rule. Okay, so I did a fairly rigorous investigation of the dynamics of dynamical systems, of the dynamics of rewrite systems involving more than one rule, and there's some really quite rich behaviour which could be observed there. But I became more and more interested in what could be done with just one rule, for a few reasons. One reason is that I think just as a kind of general principle, it's always better to try and understand the very simplest systems first. Another reason is that these simple systems can be easier to apply, and another reason is because it's kind of more shocking and more interesting if one can find exotic behaviour which is produced by, say, only one rule or something simple like that. So anyway, this paper holds a lot of technical things and interesting things which I'm not going to talk about now. I also put this little ditto on my website here, showing about how these rewrite systems work, how they can be applied to study things like Turing machines and chaos and self-replication. And also, I put a little bit at the end about these very simple systems which just involve one rewrite rule. Now, I think I've just discussed this one with you. This is one of the examples of these systems with one rewrite rule, which produces complex behavior. And here's the other one. So this actually has a slightly simpler rule, although you have to put in slightly more sophisticated initial conditions. So let's have a look what this system looks like. Okay, so now what I want to talk about is one of the most interesting and simple and kind of fascinating examples of one of these simple rewrite rules which I found. So here's how it goes. We start off with the initial condition 110, 110. And then our replacement rules are just that we keep replacing every 110 with 1 0 0 0 1 1. So here's how it goes. Again, it's difficult to see exactly what's going on when we run this thing through Notepad. But if we have a look at it through Mathematica, things look a bit more clear. So here we are. We can see our initial strings evolving. And this plot here, what this plot here shows is the string on the 19th time step. And this line here goes up by 2 whenever there's a 1 in the string, and it goes down by 1 wherever there's a 0 in a string. So in a way, this is kind of keeping track of the pattern of the 19th string generated. And one can see by the lack of regularities in this line that there's something fairly complicated going on here. Something else which is fairly telling is if one looks at these pictures here of the sort of successive states of the system, again one sees that there's a kind of lack of regularity here. It looks like something quite complicated is really going on here. Now these strings get very long very quickly, and so it soon becomes difficult to actually represent them properly. And in particular, the information on the far right hand side becomes hidden quite easily, because as these strings get longer and longer, by the way that these graphics are set up, one tends to only look at the kind of left hand side. And so what's interesting then is if one looks at these strings and just looks at them in reverse order. So we can do that, we can just reverse the order of all the strings, and this reveals something really quite interesting. If one looks at all of these strings in reverse order, one sees that there's really a fair amount of complexity going on at the kind of other side of these strings, at the kind of right hand side. And so it really seems as if these systems are really quite highly elaborate. And I think it's quite remarkable given that they're just initiated from very simple initial conditions just by doing these kind of one rule replacements. So I'd be really interested to see any further analysis of these kind of systems. I wonder if anyone's proved any kind of results which say that these type of systems have to have special kinds of simple behavior, but I doubt that they have. In fact, I would wager that these systems can probably, in some sense, produce as complex dynamics as any other systems like cellular automata or whatever else. Certainly, I imagine that's true if we allow more than two different symbols. I mean, here we've just been using 0 and 1. But anyway, I think that the whole thing is fairly instructive in that, one, this is something you can do while you've got some time to mess around with Notepad, and two, this is a fairly interesting new area of research, finding out what kinds of things can be done just using one rewrite rule. And I think it's especially important for areas like, say, nanotechnology or biotechnology, where one might be interested in making rules which make things happen or do computations, but one doesn't have the ability to be able to manipulate many objects and build Pentium chips and so on. In other words, if you want to do computing just by moving a few objects around, then I think it's very fruitful to look at what kinds of things you can achieve just by looking at incredibly elementary rewrite systems. Well, anyway, if you're interested in this kind of stuff, I'd encourage you to have a look at the talk I did on my paper, because there's a lot more about these kind of